good morning, and welcome to everyone to our ANH workshop number 31. Today, we have with us a special guest, is Daniel Rincon Martinez, a PhD, with the talk about Rio Magdalena Rofi project, lands interaction of the major tributary of the Caribbean Sea. So, remember the different talks that we have had during the year. I'd like to remember to everyone that the different talks, the videos, the recordings, and the presentation are available into our web page. Later on, into the chat, we'll be sharing the link. So remember that today, as mentioned before, we have the Rio Magdalena Rofi project, lands the interaction of the major tributary of the Caribbean Sea. Next week, on September 30th, we will have the workshop number 32, a special guest with Cesar Mora and Victor Ramirez, is the gas play fairway assessment in Colombia Basin offshore and onshore with hydrocarbon commercial production. In October, we'll have 4 different talks, starting with Andres Mesa, Brian Frost, Karina Rodriguez from Searcher, and at the end with Carlos Molinares about the hard task of increasing production and reserves in Colombia through the enhanced oil recovery, exploration offshore and onshore. In November, we'll have 4 different talks. We have a structure, a stratigraphy and petroleum potential of the deep water of Colombia Basin offshore northern Colombia. On November 11th, we'll have the structural styles within the Colombian Caribbean offshore basins and their relationship with the thermogenic hydrocarbon evidence. In November 25th, we'll have the offshore Colombia, what type of biodiversity holds underneath. So those are the areas, different areas during the year, and the different talks we have proposed and identified different gas and condensate, mainly the ones related to the Sinú San Jacinto, Lower Magdalena Valley, and some associated with oil production. As mentioned before, that's the link where you can find the different talks that have been taking place during the year. And I'm quite glad, I do have the special opportunity to present Daniel Rincon Martinez. His PhD, he's a doctor. He's marine biologist by training with a master in science, in neuroscience, awarded by the EAFIT University of Colombia. He is a doctor in things of nature with emphasis in marine biology, obtained from Bremen University from Germany. His primary field of research has been micropaleontology, particular methonic and plantic foraminifera, and its application to paleoceanography, sequence stratigraphy, and paleoecology. His research project encompasses rock form in a wide variety of depositional environments, meridional, shallow, and deep marine, and ages from Mesozoic to Neogene. Fieldwork has been undertaken in both ocean and land settings, mainly in South America, including Chile, Colombia, Ecuador, Panama, and Peru. He has 15 years of industry experience in several fields of geology. During the last 4 years, he's been deeply involved in the identification of geohazards and sea hazards on the Caribbean offshore of Colombia. So, as mentioned, next week, we'll have our special guests, Cesar Mora and Victor Ramirez, with the talk of gas play fairway assessments in Colombia Basin offshore and onshore with hydrocarbon commercial production. So I'd like to give the stage to Dr. Daniel, and thank you. Daniel, your microphone is muted.
Sorry.
Yeah, perfect.
So, good morning, everyone. Thank you for showing up. Today, I'm gonna try to socialize this field campaign that my colleagues have titled the Rio Magdalena Rofi Region of Freshwater Influence. So this is a joint venture between German institutions and Colombian institutions, mainly led by the Kiel University, Christian Albert University, and Universidad del Norte from the Colombian side. This is an effort that has been taking about 5 years to build. Actually, this cruise was planned to occur 2 years ago, but because of the pandemic, it was initially canceled, and then afterwards we received the very good news regarding its actual occurrence. So I'm presenting today what is going to happen in about one month. But before presenting that, I'm trying to give you an overview of what we know about the Magdalena Trophy and its sedimentary connections, and how we can identify the trophy, and what is the relevance for this public, that is this audience, which is today here with me, which I suppose is mostly geoscientists. So I'm trying to link what is going to happen in the water into what is the consequence in the geological record. So our agenda will talk, first of all, of course, trying to clarify what is a ROFI. Then we have an overview about the Magdalena River, and what is the expression of the Magdalena ROFI system, and what is sedimentary connections. And of course, we're going to see about the deep sea Magdalena fan. And finally, by the end of this presentation, I'm going to present our work plan for this expedition. First of all, a ROFI is what everybody knows as a river plume, basically, and it's a fresh ROFI translates as a region of freshwater influence, and it's a zone which is between the estuary and seawater. And in this area, the buoyancy of the fresh water is equal or exceeds the buoyancy fresh water comes into the sea, and how its buoyancy is equal or at least exceeds what is the buoyancy of the salt water that comes over under the freshwater plume. This freshwater is characterized by a high charge of sediment, high sediment load, and of course this extension of this ROFI depends mainly on the river runoff. The discharges of the rivers are, of course, very or heavily charged with nutrients, which affect the productivity, primary productivity in the plume. Instead, you can see here coastal waters that are not that trophic, let's say. So the interaction between these two systems depends mainly on of course, the river runoff, tides, the river buoyancy, and all this system affects not only biological communities, not only the hydrological processes here, but also the sedimentary processes around the estuaries and the deep sea fan. So why is important to understand these systems from the actualistic point of view? So as you might notice, the ROFI is normally in front of the delta, and it's a very small area. Actually, it is a very small area, but this very small area reflects an integral view of the river heart. So why? Because it integrates what is happening in the highlands, also in the lowlands, and also on the shelf. So whatever is happening here along the river, we are recording it in the ROFI system. So if we have deforestation on the highlands, so we have increased erosion, we have increased sediment load, and that will be reflected somehow in this area offshore. If we have increases in nutrient inputs into the river, then we will have it recorded over here. So it's a very nice and, let's say, economic way to evaluate the health of the rivers. And of course, it is a good record of environmental perturbations, of sea level changes, the river runoff, tectonics, climate, if it's rainy or not that much. And more recently, we can get record of the human settlement and changes in land use, as I mentioned before. So this is a very nice way to understand what's going on along the basin. And the other important factor is that it not only records what's going on the continental area, but also is the area where we transfer this information into the deep sea fan of any river or into the coastal sediments. So that's the reason, because it's the intermediate point between continent and the deep sea. In this case, we're going to focus on the Magdalena Basin. This is the most important river of Colombia for everyone. I mean, it's a very large basin. It covers about the 24% of all territory. It is a basin with the most productive economic areas in the territory. You can see that the Amazon over here is not that relevant in terms of economy. Also, the Llanos, because pottery and also the oil and gas, the human settlements and industries. It has more than 30 million inhabitants, so we all depend from this river basically, and it's very important to check what's going on there. Also, all the hydrological power is focused on this basin, including the Cauca and the Magdalena, of course, they both together. And drinking water comes from there for 38 million people. So this is very, very key basin for the country. Now, if we're going to check the river as the water body, we can say that this is one of the largest rivers. And its dynamics, this hydrological dynamics, depends pretty much of the precipitation, of course. Precipitation depends on this intertropical convergence zone. And in some part of the year, this intertropical convergence zone is moving to the south in South America. So you can see that Colombian territory is, let's say, dry. That corresponds to this first period of the year. There is a small lag between precipitation and the river discharge, but more or less it matches. And then during the second part of the year, this intertropical convergence zone moves to the north, and it will be reflected in here in these later months of the year. So you can see like two cycles, one of very low discharge, one increase, then again low, relatively low, and then the higher discharge by the end of the year between October and November. Also, this pattern is very well tracked with El Nino and La Nina phenomena. So you can see that during El Nino, most of our territory, Colombian territory, is dry. So you can see in this graph several Nino years, one here, and here, and you can see that this discharge is getting its lowest or minima during these periods. And also during La Nina, we have let's say, as is occurring this year, we have weather conditions, and then we have increases in the river discharges. So this is a very nice connection between atmosphere, land, and sea. One way to see this roughly, based on these river discharges and based on what's going on the atmosphere, is trying to check what's happening once the river gets into the coastal waters regarding salinity. So you can see here that during La Nina, so we have a large plume during the months of March, April, and May. And during neutral and El Nino conditions, when we have drier years, it is more clearly during the last part of the year, this plume becomes bigger. The rest of the year is negligible. So as you can see, it more or less matches what I said before regarding the periods of major precipitation. So another way to see the roughly is checking the temperature of the seawater. So if we have waters coming out of the river, they might have a contrast regarding the surrounding water, the surrounding coastal waters. So here, again, we have this nice example from Ana Torregrosa. So to check what happened during La Nina year, neutral year, and El Nino year. And you might notice there is not like a clear signal. So you can really you don't notice really like a plume system based on temperature. However, what you might notice is that during the first part of the year, so December, uh, uh, January, and February, you have colder waters coming from the north along the coast, and they are contrasting with something over here which is warmer. And this happens also during neutral years, and it happens also during El Nino years. So in blue we have colder waters, and in yellow we have warmer waters. Which if you can contrast this image versus this one or this one versus this one, it's something is going on. So what happens there is that we have an interaction between the southern portion, which is warmer and is divided by the Magdalena Trophy, and the northern portion coming from the Guajira area. So you can see here this upwelling system from the Guajira has some filaments that deflect toward the northwest, but also some other filaments that come along the coast with cold waters that are confronting versus these warm waters in the south, and the division point is mostly the Magdalena Trophy system. So as you might notice, the trophy is not only depending from the river and the sea uh, conditions, the coastal conditions, but also there are some other system which is coming from very far north and trying to invade this territory. So this is another factor to have in mind. Now coming back to the Magdalena River and the sediment load. So we previously saw what's going on with the water discharge and the seasonal changes in this discharge and El Nino and La Nina variability. But somehow Juan Darío Restrepo, he found a nice relationship between the water discharge and the sediment load. So the bigger the water discharge, the bigger the sediment load. That's almost a linear relationship. So when we have the minima in water discharge, we expect to have the minima in sediment load, and when we have the maxima, we expect to have the maxima in sediment load. That's when we talk about sediment load, is the sediment transported at suspended material, fine grained material, and that's the way the stream gets this color, this muddy or milky color. As I mentioned before, there is a relationship between the atmosphere and the river discharges, and so do we expect to have the same relationship with the atmosphere and the sediment load. So you can see here El Nino years in these black lines. So you can see here in these black lines we have minima in river discharge, and when we have La Nina, like for instance during this year, we have maxima, and during this other period we have a maxima, and during this other we have a maxima during La Nina year. So we have increases in sediment load regarding the season and also regarding the multi-annual situations. So what Juan Darío did is regarding the suspended load, and this is just basic theory regarding this concept. So suspended load is mostly composed of silt and clay, and as the term says, is suspended in the water column in the stream. However, as geologists, you are more focused on the sand and gravel transport, and they have a complete different way. And this is not really quantified up to date. So we have the river, and we know what's going on the suspended load, but we don't have idea what's going on with the coarser grain size that correspond to sand and gravel, and they have a completely different way of transport, which is not in the stream, but also is by sliding, rolling, mainly by traction. On this graph, you can see that this suspended sediment load, once it gets into the sea, it tends to remain larger times into the water column, and then slowly settling in the seafloor. Instead, the coarser grain size, as I showed you before, they move slowly and they try to build the deltas and estuaries, and they don't get that much into the deep water unless they have a completely different mechanism for transport. So this is more or less to have an idea uh, why what we measure on these plumes, the suspended sediment, is not exactly what we get in the deltas. Okay, so the steeper the tallback, probably we will get the larger particles that can be transported. So the steeper we can transport larger particles. Also, if we have a stronger currents, probably we will get bigger particles as well transported. And if we have a stronger currents as well, we might transport this suspended material further away offshore. So that's pretty basic concepts just to understand what we measure. So one thing is the suspended material, which mostly corresponds what we see as a river plume. This is a satellite image from May, probably. And this is another image from March, I think so. So you can see the different shapes of the plume. And again, Ana Torregrosa and some colleagues from Uninorte, they did some stations, did some measurements. In yellow, you can see like a solid plume, so you can see the strongest body of muddy water. And this brown reflects all this transition with less charge of sediments. In any case, they both reflect a plume, and this is the one with a major concentration. So you can see how the plume moves in different part of the year. And in this diagram, it synthesizes the main direction of this sedimentary plume. So from January, February, March, when the upwelling comes from the north, it is mostly deflected toward the southwest. And when the upwelling is not that present, and we have larger discharges of the river sediments, then we have the opportunity to move the plume towards the northwest. Okay, so that's very interesting because everything seems to be coupled. This is a modeling we did in the institute, ICP, Instituto Colombiano del Petróleo, and it more or less tried to reflect what's happening with sedimentary particles once they get released into the water. So this is the Magdalena mouth. In blue, you can see the particles of certain size, silt particularly, that we get placed in the water, and then the red area, it reflects
Daniel.
It seems that we lost connection. Okay, to all of the attendees, if you can give us just a moment, we're having some technical difficulties, but I'm quite sure that shortly Daniel Rincon will be back with us again.
I apologize for this issue with the connection to internet. Could you please confirm if you are seeing my screen?
Yes, we do.
Okay, so as I was saying, this is a modelization of what happened with particles once released into the coastal waters. I don't know if you listen that, but I'm going to repeat very quickly. In blue is the place where we place the particles. So in this square, you're going to see fine sands, very fine sands, and coarse silts, more or less the material that comes into the plume. And in red, you're going to see the location, the final location or final location of settlement of those particles. So I'm going to replay. So this is what happens in February, March, April, and so on. Main conclusion here is fine sands, they don't displace that much. They're still very close to the river mouth, as I mentioned before. Very fine sands, they tend to move a little bit more. And coarse silts, they definitely move a lot. Yeah. And as you might notice, they follow the same dynamics I mentioned before, moving towards the south into January to March, and then they start to deflect towards the north during the final part of the year, according to the winds, the upwelling influence, and the river discharge. So following this line, I'm going to replace a different way of seeing this. And in the colors, you're going to see the depth at which these particles are settled. So again, this is fine sands. This is very fine sands and silts on this area. So you can see with silts how they move very, very large distances, more than 10 to 20 kilometers, and they tend to stay settling in between 400 and 800 meters depth, water depth. If we watch these fine sands, they stay very close to the mouth, and they don't settle deeper than 400 meters on the year. Very fine sands, they move a little bit more than sands, between 10 and 15 kilometers, and they tend to settle in about 400 meters water depth. One very remarkable data is that these fine sands, they take between 5 to 6 hours to reach into the bottom. So once they get released into the plume, they will settle in about 5 to 6 hours. Very fine sands, they will take between half day and 1 day to get settled into the bottom. And the coarse silt, it might take between 5 to 7 days to get settled. And in some cases, they won't settle because of the turbulence of the plume and the hydrodynamics of the water column. So this is like the connection that we have with the sedimentary processes. And I'm going to give you like a new view of how the modern Magdalena deep sea fan is fit. So this is the same model that I showed you previously, but I'm gonna just play the place where they settle. So in blue is the placing of the fine sands, in yellow is the very fine sand, and in red is the silt. And these are the canyons. This is the Magdalena River mouth, Barranquilla, and these are the canyons that are just very close to the river mouth. And you're gonna see where these particles end up after being released by the plume. So during February, you can see how they get onto this area. They get into this canyon. They are in front of the Ciénaga Grande for most of the year, at least half the year. And then by the end of the year, they get very far, just in front of the Magdalena. So you might notice that the platform over here, the continental shelf, is wider on this area and is narrower on this area. And it might be related to the place where these sediments are being settled. However, one of these very important situations is You might notice how they end up feeding all these canyons, and we're going to do this connection later on. The next situation associated with this is we get all those particles released into these canyons. So this is the Magdalena River mouth, and then these are the canyons where those particles were settled during the first part of the year, and as you might remember, they try to settle over here, over this area, on the final part of the year. But what is important here is you might notice that this is straight connected to the river mouth. So it's in this part of the modern delta of the modern fan. And Javier Hidárraga from Norte, he did a very nice geomorphological work on this modern fan and the upper fan, and he proposes these canyons as the main conducts for sediment transport into the deep sea, which might be completely right, even though these other canyons, they are not directly connected as this one. You notice that most of the sediment released in our model, they tend to get settled over here and even here. So this model might be right once they get into this canyon in a matter of let's say turbidites. They start feeding some piggyback basins over here. They find some obstacles, of course, which are related to the formation of the folding of the seafloor, the structural deformation. So they get obstacles, they get areas of deposition, huge areas of deposition associated to many of piggyback basins. And occasionally they might find some way to escape these obstacles or to erode them and continue the way up to the basin, the Colombian basin. So this is very nice situation because it reflects very well the modern dynamics with the ancient one. In the other side of the delta, we were here in front of the Magdalena River mouth. Then we're going to move over here. The other side of the modern fan is very different. You might notice we don't have these canyons. We don't have a straight connection with the River Magdalena, but still we have a lot of channel levee systems, and also they are mainly intercalated with mass transport complexes. So one thing that is relevant here is how this interdigitated system between channels and mass transport complex, they also contribute to move sedimentary particles from the shelf towards the deep sea. Occasionally, this is another work from a colleague of mine in the Institute, Darwin Mateus. He did a very detailed mapping of these mass transport complexes in the older part of the Magdalena River fan. See, this is the modern one, where we're checking this straight connection with the canyons, and this is the other part of the river fan, which is characterized by these channel levee complexes, but also there are a lot of landslides, different types of landslides, from rotational to translational, and also complex slides. And they are all intercalated in a very complex system with the mass transport complexes. In this area, the feeding of the particles to the deep sea is not occurring by river sediment loads and then transport through turbidites across all these canyons. It occurs in a different way. It occurs by instability of the slope. As you might see here, we have a lot of evidence of this instability on the shell break. And apparently what's happened here is that we have like an ancient topography. Somehow it gets unstable, and finally we lose all this sediment over here, and we end up with a relief, something like here. And that means we have a very erosive system, which is obviously is reflected by these very large mass transport complexes over here and all the these initial signals of erosion and instability on the upper slope. These systems they of mass transport they are not only modern, they've been found also in previous times. So you can see here a comparison made by Leslie and Mann. So we have more or less the very same bodies of mass transport complexes, these orange ones, and they are comparing size versus Pliocene mass transport complexes over here. So this is the Santa Marta mass transport complex, this is the Barranquilla mass transport complexes, and this is Cartagena mass transport complex. So you can compare them, and you can see that they are really giant compared to what's going on. But of course, they are not novel into the area, and it's a process that is continuous and is occurring right away. So we can compare the ancient versus the modern fan, and this is for this area, the ancient fan is more or less a soft or smooth topography. So we have an appearance of low structural deformation on the surface. But then we check in the seismic, we have a lot of folding of the strata, pretty much as if occurs on the modern one. So you can see this line and it reflects these anticlines and piggyback basins over here. And it's more or less what we found here, but deeply buried, and also they've been degraded, eroded by these flows that I showed you before, the mass transport complexes, that they've been softening the slope topography. In the modern canyon of the Magdalena, we have this feature over here, and when we check what's going on, this is a work of a colleague of mine, Julian Naranjo, from the Institute as well. He was able to check how this Magdalena Canyon is being aggradational in a vertical situation of about 1,000 meters. So that's a lot of aggradation for this canyon. Very interesting fact as well. So the ancient system and the modern system, they compose this very huge deep sea fan that you might see here, and was depicted by Javier from the Norte. And he proposes that the farthest limit of the fan is basically constrained by these topographic heights of the Columbia Basin. So otherwise, probably this fan will extend pretty much over there. There is a comparison here of the sizes of some other fans versus the Magdalena area. So it's not small at all, it's very large. And we can check something of its evolution. So this is a work from us, from Ecopetrol. It was published as well. And this is isocore maps. This first image corresponds to, let's say, part of the early Miocene and the complete middle Miocene. And that means that this is the thickness of the sediments that have been accumulated over this time period. So this is when we try to extrapolate the time and the thickness, we get some estimation of the sedimentary transport into this area, and it more or less mimics what is going on with the modern Magdalena River. So their sedimentary rates are more or less equal. So this is the first sequence where we have record of South American, let's say, source material into the Colombian Basin. So you can see here Barranquilla, and here we have Morrosquillo Gulf. You can see here large accumulation of material. And then we have, this is the South Caribbean Deformation Belt. We have also a large deformation, a large accumulation of material out there, very far from the continent, of course. But you have to bear in mind that by plate tectonics, this is not the actual location of this sedimentary basin. Probably it was located further south and might be associated with this part of the continent as well. We are not that sure, but probably it's associated with this part of the continent. Then during the late Miocene, the sedimentary rates they get lower, and probably by this time we get the Proto-Magdalena River arriving to its modern mouth, closer to Barranquilla, probably. So we can see here the highest sedimentation rate very close to Barranquilla, and also they still spread along this southern Caribbean deformed belt, and we can get also somehow the very same shape of the Magdalena deep sea fan. Then later on, in the early Pliocene, during the Sanclan and part of the Agencia, we expect to have the joint of the Cauca and Magdalena rivers. So finally they get together, forming a single basin, and then we have a huge increase in the sedimentary rates that equals 3 times that what we saw before in the sequence 2. So that's 3 times what we get in the late Miocene. And they also located slightly to the north of Barranquilla and slightly to the south of Barranquilla, especially in what we call the ancient fan. Then later on, during the late Pliocene, we have a situation similar to the modern. So their sedimentary rates are more or less the same. And by this time is when we get these giant mass transport complexes, Barranquilla, that I showed you some slides before. They are located somehow over here. So they are incorporated into these isochord maps. Then later on, we have in the Pleistocene, we have again an increase in the sedimentary rates. So you can compare the sedimentary rates of this time versus it's almost the double of the modern one. So this is one of the biggest sedimentary rates by the early Pleistocene. And then during the same period, we get the biggest or the largest sedimentary rates of all times during the Neogene. And this is almost 6 times when we get into the modern river delta. So you can see here these huge accumulations to the south of Barranquilla, in front of Galera Samba. So probably associated with this ancient fan that I mentioned before. And then we start to have some very nice thickness over the south, very close to the Urabá Gulf. And this picture is more or less the same. We start decreasing by the late Pleistocene, we start decreasing slightly the sedimentary rates, but they are more or less the same as the modern river. Finally, for the latest Pleistocene, Holocene, and so on, we have a huge development of thickness associated with the Gulf of the Atrato River and the Gulf of Urabá. That's the most dominant feature, but that doesn't mean we don't have support or input from the river, from the Magdalena River. So finally, with the expedition, this is the ROFI. Some of you have seen this news on the paper. Our goals are assess the extension and dynamics of this tropical river plume. So we're going to talk about dimensions, stability, extent, mixing conditions, the structure of the salt wedge, the total suspended solids, and the pycnocline dynamics and turbulent processes. That's regarding the hydrodynamics of this river plume. But also we want to quantify the past and modern sedimentary connections between the river mouth, the delta, and adjacent coastal zones with focus on human impact on morphological changes and nutrients and pollutants balance. So we would like to track where the human start to have a real influence on the river. And finally, we would like to explore hypotheses regarding what is the real interaction between the ROFI and the Guajira Valley system. Because of that, Germany has placed this very nice ship. This is the youngest of the German fleet, reserve fleet. This is the Maria Merian. It has capacity for 23 scientists and 21 nautical crew. It has equipped very modern equipment to get what we're gonna do. The ship is gonna arrive very soon, in less than 1 month or 1 month from here. And it's gonna be here in the 19th of October, and it's gonna depart from Cartagena the 20th of October for a total time of 26 days of working in front of Colombia. We have several research questions. One of them is how the plume behaves. What is the extension of the Magdalena River plume? How far it gets? How are the processes that occurs below the surface? How they interact with this interdigitated system of coastal waters? So because of that, we would like to explore the structure and dynamics of this mixing zone and the turbidity maximums of the river in different tidal scales. We're going to use this sort of equipment. This is a lander. The lander is going to be placed in front of the mouth of the river and is equipped with IDCP sensors and some other sensors that they will be able to track all these hydrodynamics variables and try to let us know how the river behaves when it's stronger, when it's weaker, because of the winds or because of the tides or because of the river runoff. That's very interesting. And this device is going to be placed there while the ship is moving all around the study area. On the ship, we're going to have this ADCP, it's a catamaran, acoustic Doppler current. It's going to be tracking the whole behavior of currents. We're going to do CTD measurements. That means temperature, conductivity in replace of salinity, and depth, measure as pressure. And we're going to take a lot of sediment of water samples. And also we're going to have a micro structure sound that allow us to understand some other variables of dynamics. Also, regarding the suspended sediments, we would like to know what are the hydrodynamics behind this sediment settling that we try to model, but we don't know that much about the real behavior of these hydrodynamics, and how this aggregation of individual particles contributes into the settling, and of course the clearance of this plume, the faster clearance of this plume. So because by doing so, we're going to take water samples using in situ laser particle sizer to establish grain size. And we try to use in situ flow camera to understand what sort of particles are floating on the water column. Also, we would like to know biogeochemical processes in the water column. So that is knowing what is the effective role of the nutrients that come in the water column and how they distribute into the rough system. So that's part of understanding the modern anthropogenic contribution to the coastal waters. So that's one way. And also we would like to know what is the influence of these nutrients on the phytoplankton and zooplankton communities. There's an effect on the biological communities. And finally, what is the relationship between this phytoplankton with the chlorophyll and the zeston? And what is the final impact on the primary productivity, thinking on CO2 sequestration by natural systems? So by doing so, of course, water samples, we're going to do some chlorophyll analysis by fluorescent methods, analyzing of phytoplankton and zooplankton communities on the microscope, and so on. So this is, I would say, this is not that basic research. This is very challenging research facing the anthropogenic effects we have nowadays on our ecosystems. And not everything is just science. Everything must be applied somehow. Also, something that we would like to know is knowing what are the main geomorphological features of this river delta and upper fan. And by doing so, we're going to do multi-beam echo sounding and also parametric sonar to know the subsurface structure. And as this is going two ways, like one way offshore and one way back to the shore, we try to explore if there are some migration rates of the river forms. So we will try to know if when we move out and then when we come back, something happens during this transit on the seafloor shapes. This is a nice example from Diego Madrid from Fit University. He did a thesis and he tried to compare what's two images from two different years in the Magdalena River fan and delta. So he compared 5-year difference images, and you might notice that in green we have areas where sediment got accumulated. In red, you get erosion of sediment. So this is a nice way to see it in a larger time scale, and we try to check in a shorter time scale as well. Also, we would like to know what is the link between the fluvial input and turbidic currents. That's the reason because we're going to take some gravity color sedimentology. This is a work by Gloria Romero. This is the thesis of Gloria Romero. And she found 3 cores in front of the Magdalena mouth. This is the upper fan, I would say. And she was able to identify like cores with evidence of turbidite systems. So this is one body of turbidite, the Boma sequence, and this is another one. And she was able to evidence that, in fact, a lot of the transport of the motor data is done by turbidite currents. Also, we would like to know the modern connection, how the sediment is changing downslope. So we're going to take a giant box color and doing some multi-section core logger and the whole sedimentology pack for all this stuff. Also, the near bed processes, which is also important, is how these bed sediments are linked to the suspended load I mentioned before. I showed you 2 different mechanisms. One is the suspended load on the water column, and the other one is the one settled and the one which is transported near the bottom. So we will use again the lander and giant box cutters to check the sediments and try to understand what is the connection between the water column sediment settling and if they more or less reflect the population of sediments which is already settled down there. What is the influence also of the tidal cycles on these seafloor features? If they provide, like, let's say, sediment waves, helping to the transport or not, and what are the magnitude of frequency of these turbulent events. By turbulence, I mean the turbulence which is on the water column, not near bed, or if we can track it by this lander device, that would be nice. Also, biochemical processes, and by biochemical processes, something that we still don't understand well, how our deep systems get sedimentary organic matter, which is useful for generating hydrocarbon systems. So we're going to use same material, giant box core along downslope, and we're going to use evaluation of total organic matter, organic petrology, checking probably bacteria which is arriving down there, and trying to understand what is the quality and amount of this sedimentary material that comes out of the river or comes out of the shelf and gets deeper systems to get like a modern analog of what we get into the Southern Caribbean. So more or less, those are the questions that we have. And don't forget that this is something quite novel, checking the relation between the rough system and the upwelling is being documented by satellite images, it's been documented somehow by other people, but we haven't yet explored the sedimentary record of this interaction. So this is another way of approaching and using the information we're going to have. By doing so, we're going to do some isotopes with mass spectrometry, doing, of course, the sedimentology, water samples, trying to understand what is the signal, the biological and geochemical signal of the cold waters, and what is the signal of the river water, and try to establish if we can get a geological record of it. So these are more or less the transects we're going to take. So Barranquilla, we're going to do some transects into the north, trying to follow the geomorphology. You can see here in purple colors some geological maps. And so we try to follow also the La Aguja Canyon, and we're going to explore some of the Rancheria Canyon as well, and try to do this north to south transect, establishing what is the divisory line between the upwelling of the Guajira and the river delta. So in hydrodynamics, we're going to take all these transects, and we do 6 IDCP transects and 45 CTD profiles and water quality measurements. In terms of sedimentology, we're going to do 4 multi-beam and subbottom profiles, 3 in the Magdalena area, 1 in the La Aguja, and we want to try to take 40 samples of surface sediments and hopefully 18 gravity cores of up to 10 meters. In summary, this expedition has been a collaboration between Germany and Colombia. We hope 6 institutions participate deeply in this research. The team on board will spend 26 days on sea. We're gonna run for more than 1,500 kilometers. We expect to take 18 sediment cores, 14 surface sediment samples, 45 physical and biochemical samples. And finally, I would like to thank these 2 guys, Professional Christian Winter, which is the leader from the German party, and Oscar Alvarez from Uninorte, which is the leader from the Colombian party. They both put together all this team. They all both have coordinated extremely well this expedition and placed everyone in the right side for a joint purpose. So I would like to thank them especially and my colleagues from this expedition. Thank you very much.
Thank you, Daniel. It's been an amazing presentation as always. And there are a couple of questions from one of the attendees. And if any of the other attendees got any questions for Daniel, remember that in this very moment, we start a brief Q&A session. So I will start with the first question by Dr. Luis Carlos Carvajal. Greetings to Luis Carlos. He said, excellent presentation, Daniel. 2 questions. The first one, is the Magdalena River the main contributor for the thick deposition in the Miocene observed in the Northeast? Or is there any other element, like, for example, the uplifting of the Santa Marta Massif or Massif that can add sediments during this time? That's the first question. And the second one is, any plans to use OBNs to understand the velocity of the currents formed on the canyons? Daniel, since your microphone is off.
Sorry. Thank you, Luis, for your question. I apologize. You're right, and this is a very curious fact for us. As you might notice, this is in front of the Southern Caribbean Deformation Belt. This is not close to land, no way to get close. So one of the explanations we did with Eduardo is that backtracking of the Caribbean plate will place probably this area further south. So we speculate that might be located about here. And then the source for the sediments will come in the very same system, let's say north and southern drainage system coming from the north of South America. That's one explanation. And the other one, as you mentioned, is that this area is not that far into the south and may obey to this Santa Marta massive. That might be another explanation. Unfortunately, no one has drilled this area up to now, so we have no idea what the provenance of these sediments is at the moment. But that's a very interesting question to be solved in the future. Definitely, you're completely right. And then secondary, regarding your question of the velocities and the tallback of the canyons, yes, this information is quite important. From the Institute, we've been working on some modelings of turbidites, and we found that for this canyon, we have velocities of turbidites of about 20 meters per second. That's a lot. That's very large, but it's just a modeling. So hopefully this cruise will allow us to get real data to provide further evidence of what is building these very deep canyons on the Caribbean, probably, and very deep and also very clean because it's most erosive. So probably we will get that evidence from this cruise. Thank you.
Thank you, Daniel. Is there any other question from the attendees? Okay, meanwhile, we give them a moment. I'd like to remind to all of you that next week we will have a very interesting talk that's going to be given by Victor Ramirez and Cesar Mora. The title of the talk is Gas Play Fairways Assessment in Colombia Basin Offshore and Onshore with Hydrocarbon Commercial Production. Okay. Daniel, it seems that we got no further questions from the attendees. So I'd like to thank you.
Okay, thank you.
For this amazing presentation. Of course, in the ANH and the whole country, the geological community will be expecting the results of that magnificent expedition that you got coming ahead. So I'd like to thank Luis Carlos for the question, and I'd like to thank to all of you for the attention of today, and see you next week. Thank you very much.
Okay, have a nice day. Bye.
Right, have a nice day. Bye.